All right. Now I'm recording.
Yeah.
The question was, did mine is from modern algebra, and it is, but I picked this one because it also has roots in number theory, which is what I prefer. So I actually proved Fermat's little theorem 2 different ways, but when I timed the presentation, I don't have time to go over the number theory one because I figured I needed to stick with the modern algebra one. So I'm going to share my screen, hopefully. Can you guys see that? Do you see my OneNote?
No.
I still see you.
Okay.
Yeah.
Then that didn't work. Oh, there we go. Now you should see my OneNote.
Yep, that worked.
Okay. So a brief bit of history before I dive in. So Pierre de Fermat was a French lawyer who lived in the 1600s. He first wrote this theorem in a letter that he was writing with Frenicle de Bessy in 1640. And of course, in apparently traditional Fermat style, he said the proof is too long to include in this letter. So no written proof was ever found of his. The first published proof was in 1736 by Euler, but in some handwritten notes, Leibniz also proved it in 1683. Anyway, so here is the proof from number theory that if I have time, I can go back to it, but I really wanted to focus more on the abstract algebra, the modern algebra side of it. So I can come back to that if I need to. But, all right. In abstract algebra, so we are going, if A is in Z, then P is prime, a prime number not dividing A, then P divides A to the P minus 1, that is, A to the P minus 1 is congruent to 1 modulo P for all A's not equivalent to 0 modulo P. So I have some lemmas right here and corollaries that I will reference as I get to them, but I wanted to have them typed out so I didn't have to write them. So our proof by congruence here, we are going to assume that P is prime. And that P does not divide A. So then every integer is congruent to 0, 1, 2, 3, all the way up to P minus 1 modulo P. So we are not going to look at the 0 congruence class because those are multiples of P. And I don't care about multiples of P right now. We only want to pay attention to the ones where they're not multiples of P, so P doesn't divide A. So that's where we need to spend our time. So we got to do this by cases. So case 1, here we need to prove that none of the congruence classes are 0. Just because I said they weren't 0, we can't go with that. So, of course, by proving that they're not 0, we're going to assume that 1 is. So R is just some integer, and A is the base that we have up here. So R times A, we're going to say that is congruent to 0 modulo P, where P is prime. Then that means that P divides R times A, because 0 is the congruence class of all the multiples of P. And that is by lemma 3.4, which is referenced up here. That's the first one. But this isn't possible because P does not divide A, and R is less than P. So therefore, P cannot divide R times A. So that tells us then that these are not the zero congruence classes. So then case 2, we need to prove that the congruence classes are different. So we're going to use R times A and S times A, where R and S are just integers. So we're going to set up some inequalities, that 0 is less than R, which is less than P, and 0 is less than S, which is less than P. What we really want to show here is that R times A is not congruent to S times A modulo P. So we will do the subtraction here, R times A minus S times A. We'll factor out the A times R minus S. And by assumption, we know that P does not divide A. But does P divide this? Can P divide R minus S? So let's go back to these inequalities right here. So we'll keep this first one the same. And then I will multiply -1 times the second one. So that becomes 0 is greater than a negative S, which is greater than negative P. So I will change those so the inequalities are going the same way and write them over here on the left. So negative P is less than negative S is less than 0. Then I will add them. So we get negative P is less than R minus S, which is less than P. But we know that R minus S does not equal 0 because they are distinct congruence classes. So therefore, that means that P does not divide R minus S. And that A times 2A, or I guess A, 2A, 3A, not times, all the way up through P minus 1A, those are all incongruent to each other. And that is lemma 4.1. Now, the lemmas and corollaries that I referenced, the numbers that go with them, those are from the number theory textbook. That textbook actually did a much better job of breaking down and referencing corollaries and theorems that were used to prove later theorems. So that's why, even though this is a modern algebra proof, my references are the number theory textbook. So this means that they're all these are just a rearrangement of congruence classes. So that means we could just write it as A times 2A times 3A, all the way up to P minus 1 times A. That equals 1 times 2 times 3, all the way up to P minus 1 modulo P. So when we look at this, it's really just each side is independently has factorials in it. So this is P minus 1 factorial times A to the P minus 1. And the right-hand side is just the P minus 1 factorial modulo P. Now we know that P does not divide the P minus 1 factorial because P minus 1 is a product of all the integers that are less than P, and P is prime. So then that we know p minus 1 factorial and p, that they are relatively prime to each other. And that is by corollary 451, which says if a, b, and c are positive integers such that m is greater than 0, that c and m are relatively prime to each other, and it gives the congruence classes. Come on screen. So that was corollary 4.5.1. So then we have this, I'm just going to rewrite this equation again. P minus 1 factorial a to the p minus 1 equals p minus 1 factorial mod p. So we can cancel those two out. Then we are left with a to the p minus 1 is congruent to 1 modulo p, which proves the theorem. Now I have a few examples. Check my time. All right, I'm at 9 minutes. All right, there they go. Examples. So to actually use the theorem, that this first one here is really simple. So p is equal to 7, and the theorem says that a to the p minus 1 is congruent to 1 modulo p. Did I write that right? So if p is 1, or I'm sorry, p is 7, so that is 3, because I'm using a is 3. 3 to the 7 minus 1 is congruent to 1 modulo 7. So, but we want to know what is 3 to the 6th. Well, 7 minus 1 is 6, conveniently. So 3 to the 6th is really congruent to 1 modulo 7. And then I move on to another harder, a little more in-depth example. Really, we want to show that this gigantic number, a number that we would not want to put in a calculator, is that divisible by 11 or not? So if something is divisible by 11, then it would be a 0 congruence class modulo 11. So we need to find out what is the remainder, basically. So this is our p, is the 11. So we need to get something so that it's in terms of 2 to the 10th. So now we got to play with the rules of exponents. So we get 2 to the 10th and raise that to the 1,121st and multiply that times 2 to the 3rd. Now that I chose because you multiply these exponents, that's where we just come back to like basic algebra 1 times 10, and that is the 1, 1, 2, 1, 0. Well, we need to get this 3, so we added 2 to the 3rd, because that...
Wouldn't it be 1120? Or am I missing something? No, you got it right. Sorry.
Oh, that's all right. Check me. I make my mistakes in the simple stuff.
No, I didn't realize you put 2 to the power 10 in the first bracket and then raised it to 1,121.
Yes, and really this, to get used to using this theorem really only comes with practice, that you get used to finding things and seeing things, because this looks really strange. You're like, why would you do that? Well, that's because this 2 to the 10th is really congruent to 1 because of the theorem. So this becomes 1 to the 1,121st power times 2 to the 3rd. So this nicely reduces to 1, making those horrible big numbers so much more manageable. But I forgot this part of the problem. So there's a -1 out there. So we'll bracket this, which that doesn't change what was written in here. -1 So then we're left with 2 to the third minus 1, which 2 to the third is simple. That's 8 minus 1 equals 7 modulo 11, which then tells us that this gigantic number, 2 to the 11,213 minus 1, is not divisible by 11 because there's a remainder of 7. All right. I have one more detailed example, but I don't want to run out of time. So does anyone have questions?
Hi, Kathy. It's Erica.
Hi, Erica.
Yes, I had a question for you. So, given that you can use this theorem and it always holds true if P is a prime, but it also holds true, right, sometimes when P is composite, do you think it's better to use this theorem for like primality checking, or would you go with something like Wilson's theorem?
That's where I think that even bringing in Euler's-Tochin, however you say that theorem, his is probably far more useful because Fermat's is very specific. It has to be prime. And we don't always know, like if it's a giant number, we're not going to know right off if it's prime, where Euler's doesn't care so much.
Yeah, and then with Wilson's, you can go a little bit more in depth. So I was just wondering, but yeah, thank you.
Sure.
Hey, can you, Fermat's theorem is pretty much saying a to the p minus 1 is congruent to 1 modulo p.
Yes.
We don't, if that statement is true, it's not necessarily true that p is prime. We know that is always true if p is prime, but we can't go the other way around, can we?
No, we can't.
Okay.
No, that's why all the problems that I've seen, now granted, I'm not into cryptography and all that, which is really where this has a lot of usage for like check digits and stuff. The examples I see have numbers that we know are prime.
Yeah, you'd use the totient function to sort of tell you what that p is if you're not sure that it's prime.
Yeah.
Okay.
Hey, Kathy, it's Michael here.
Hey.
Hey, do you believe there's any other way to prove this? Maybe by like induction or the use of Lagrange's theorem?
There are actually so many ways to prove this that I'm going to scroll back up. So I went for the modern algebra approach and proved it there. But initially, I have the induction proof here, and that uses the binomial expansion and definition of a binomial coefficient. That one, because I like number theory. That's my favorite. So I was hoping that I had time to present that one, but I wouldn't. But I saw other examples that use like beads, and some use Lagrange. Some other examples. Oh, there were at least 6 easy examples I saw on proving this theorem. So that really surprised me at how fundamental and basic it is when there's really that many different ways to prove it.
Yeah, I was going to say you did a remarkable job capturing the essence of, this proof itself, but there seems to be so many different ways to do it. And someone else kind of touched base on my first question of how this relates to Euler's totient theorem. So great work.
Thank you.
Hey, Kathy, it's Rakesh.
Hey.
Hey, I had just 2 questions. One of them was regarding the proof. What if in the proof it has stated that A was prime instead of just being a set integer? Like, how would that affect the proof? Would it still be congruent to, would A to the power of P minus 1 still be congruent to 1 mod P?
The only stipulation on A is that P can't divide it. So A can be prime, A can be composite, It just, P has to be prime and P cannot divide A. Other than that, everything's fair game.
Okay, so if A and P were both the same number, then it would fail automatically.
Yes, because then P would divide A.
Okay. The second question I had was, we're doing the examples,
Okay.
how you broke the one with the 2 to the power of like 11,000.
Yeah.
13. How did you know exactly how to break that down? I remember doing it in, was it modern algebra? But I forgot steps down and how do you know what's congruent to one mod P to make it much more easier to solve.
Right. And that's where looking at these big numbers can be overwhelming, but really you just have to focus right here on what is P, because your P minus 1, which in this case is 11 minus 1, and that's 10. So that means somehow we have to get something to the exponent of 10. So in this case with the base 2, I knew I needed to get 2 to the 10th somehow, and it did not matter out here how big this giant number could have been, because it was this was then gonna be 1, and that would make essentially that whole term go away.
Right. Okay.
So it was starting with remembering what the P is. P is 11. So then our P minus 1 being 10, get something to the 10th power, in this case, the 2 to the 10th, and then just go from there. So out here, you saw that I had to add this 2 to the 3rd because I couldn't quite get all of it. It was like a remainder.
Right. Right.
And 2 to the 3rd is so much easier to deal with.
Oh, yeah, it definitely is. All right. Yeah, that's all I got. Good job.
So for your proof, can you scroll up to proof?
Yep. Do you want the modern algebra proof?
No, this one, yeah, modern algebra. But I found it interesting that you used the modern algebra proof, but the lemmas are from number theory.
I know. That, of course, I tried to start with number theory because that's my favorite. But when I was going through and I had researched the congruent proof, which to me, the congruence speaks to the modern algebra side of it, that I found it quite funny that the proofs that I saw weren't referencing these corollaries or these lemmas, that I had to go find where they were backing this up from. So I love the number theory book. It's a great book with great examples. The modern algebra book just seemed to leave a little something to be desired. So I had to combine sources and figure out where the truths were coming from.
So the proof you have presented, it's a hybrid one, or the source is a modern algebra book?
It's a hybrid of sources.
Okay, impressive.
Any other questions?
Abby, this is Rachel. Can you hear me?
Yes, I can.
So I didn't take number theory. Are there ways to prove it without using the number theory?
Oh, yes. Because in modern algebra, you learn induction.
Yeah.
So you can, even though that's a number theory concept, you can still use it from what you learn in modern algebra. And even in real analysis, which I'm also in right now, they touch on induction. So induction is covered in a few different classes. But it's
unfortunately my modern algebra book didn't include a proof for this theorem.
Mine did not either. I had to get the proof from number theory and the internet.
Are there other applications other than you've shown? I know those were pretty much the ones we covered in my modern algebra course.
The like real world applications are beyond my comprehension. Because those are in like cryptography and dealing with prime numbers, and I teach high school math. So I don't know.
Okay.
The harder
Thanks.
example that I didn't get to deals more with
Yeah.
manipulating within congruences. Different. Yeah, so there was a harder example, but it illustrates the same thing, just with more thinking involved. That we didn't miss anything by not going over that one, but there are more details available.
Okay. Thank you.
You're welcome.
I wanted to ask one last question.
Sure.
You had the example where you're trying to show the 2 to the 11,213
Yes.
is divisible by 7, or by 11, sorry. What if the question we're asking you to show that it is not divisible by 12, for example, since 12 is not a prime number? Would you be able to like show that it's not divisible by any of the prime factors of 12 or something like that?
I'm thinking. I don't see why that would not work. That seems like that would be a lot of effort, though. But if it's
Okay.
if it's divisible by the prime factors, it should be divisible by the composite of those.
Yeah.
But I had not thought about that.
Okay. Thank you.
Sure.
Hey, Kathy, James here.
Hey.
Hey, have you run into this one anywhere else other than modern algebra and number theory?
No, those are the only two places that of the classes I've taken that I had seen it. That I first was introduced in modern algebra. I took that in the spring, and then I saw it again this summer in number theory. And those are the only places I've seen it.
All right.
You might see it in cryptography, but we don't typically take that. But
Oh, yeah, it would. I would guarantee that it would be in there, maybe as
Yeah.
an intro, but it would be there.
yeah,
That would be so cool if we could take that class.
they should really
Yeah.
offer it.
Yeah, I have a few more on that list. Graph theory being another one.
Yeah, there's plenty of things that I want to learn when it's just fun times to learn rather than an objective.
So I think a couple of people spoke about the textbook for this one, and that is the last course I'm missing. So you guys kind of scared me. Who's the author of that book? Do you know? Is
For
it
which course?
modern algebra, abstract algebra, Frale or something?
Yeah, it is John B. Frawley.
Okay.
Yeah.
I used the 7th edition when I took it in the spring.
I kind of Googled some other universities, what do they use? Even IU Northwest doesn't use that book.
Oh,
There is a book by Gallian, which seems to be very good and a lot of examples.
see, and that's why I like the number theory book, because not only did they give the proofs, the details, the abstract, they gave lots of great examples, where I find that the modern algebra book didn't satisfy that part of it for me. Has everyone gotten their questions in? I want to make sure everyone's gotten their required one. I will take that as a yes. Then, all right, then set my computer back up. Got to get the required mugshot of me again. All right, turn off the sharing. All right, I am stopping the recording.